Continuing with 5.2, okay, and of course, we're coming back from the exciting lecture we had after the test, all right? Example. We're doing U-subs, more U-subs. Let's see, U-sub should have been here. All right, integral of sine of 2x plus 1 dx. All right. Now, in principle, this is one of the more basic U-subs. In fact, I would allow answer only in this case, and I'll explain why in just a moment. All right. Now, well, let's start by doing a U-sub. Right. Let U equal. All right. Because bear in mind, we're not just integrating sine of x. Okay. We're integrating a composite function here, and it's very often the case that we'll use U-subs when we see things like composite functions in the integrand. All right. Let U equal what? I want U to be an inside guy. Okay, 2x plus 1. All right. Wait a minute. What's du then? Well, what's the derivative of 2x plus 1? 2, and then dx is differential form. All right. If U is 2x plus 1, du is 2 dx. All right. Now, there are two ways to look at this. All right. Well, right now, I don't see a 2 here. That doesn't count. I don't see a 2 in here, so I can insert 2 as a factor. I call this compensation. So integral, well, I do like this, sine of 2x plus 1, all right, times, I'll put the 2 over here, all right, 2 dx. Now, it would be lovely if we could change problems just if we felt like it, okay, but I would like to retain equivalence here. How do I pay for the 2? 1 half. Okay, may as well put it out here. All right, you agree these are equivalent, right? I will not change the family of functions when I do this. These are equivalent. We'll get the same answers. All right, so what do we get? We get 1 half integral. We're going to go to U now. Remember, you should avoid having two different variables in the same integral, okay? So you should be either in all x or all whatever, all t, all theta, or all u. We're going to go to U now. Okay, what does sine of 2x plus 1 become? Sine of u. What's 2 dx? 2 dx is du. Right? 2 dx here becomes du. And you agree that's a lot easier to work out, right? 1 half integral sine of u du. Okay, that's one of the purposes of the U-sub, to make the integration problem easier to evaluate. All right, let's do this. Equals. All right, now I'm going to unravel that integral sign, delete the du, put what at the end? Let's see, don't forget that. May as well do it early. Okay, as soon as you remove the integral signs and that b blah stuff, then put in that plus c. Okay. You might want to start by putting a plus c at the bottom right, just in case. We have 1 half here. All right. Now, whose derivative is sine of u? Negative cosine u. Okay. So we actually do get a sine flip when we integrate. Now, when we differentiate, but when we integrate sine of u. All right. Okay, let's kill 2 birds with 1 stone. The negative 1 factor pops out. Negative 1 half cosine of u was 2x plus 1. All plus c. If you want, the c could often could also be out here. All right. Negative 1 half cosine of 2x plus 1. All plus c. All right. Question. Okay.
How'd you get the 2 for du?
All right, so here's a way to look at it. We start with this. Okay, du dx, all right, the derivative of u with respect to x, that's Leibniz form. The derivative is 2.
Oh, okay.
Okay? In differential form, we have du equals 2 dx. Now, are we multiplying both sides by dx? Some professors say, no, that's not quite the right thing to say, but still, this is differential form. Right? Du is 2 dx. So, whatever, if you have a small change in x, then du is about twice that. All right. Let's see. Anything else? Okay. How can I check this?
Take the derivative.
You take the derivative, right? And if you get the derivative of this, you better get the integrand, right? So you can take the derivative to check. All right. I have a couple of comments to make. There's a second method I mentioned, which is, let's say that you don't like compensation. Let's say that you like to go to u pretty quickly. All right? There's another way to do this. You could ask yourself, well, what does dx become? All right? Well, if you look at this, du is 2 dx. That means that dx is half du, right? dx is 1/2 see that you can go from here to here pretty directly, right? Sine of u, okay? dx is 1/2 du, okay? So dx here becomes 1/2 du, okay? Sometimes that's faster, especially if the derivative here is pretty easy. All right, that's my first comment. All right. My second comment is, for a problem like this, I would accept answer only, in which case you could do guess and check. I call this guess and check. On this kind of, okay, Paul, go ahead.
Can we go a little deeper on that second method? Because I'm kind of...
Okay, so very quickly, how do we get from here to here directly? Let's say that you don't want to compensate. You want to go from here to here directly. Okay. Now, this method of solving for dx, that's especially nice if your derivative here is easy, like a constant, for example. All right. What I'm basically doing is I'm solving for dx. All right. When I solve for dx, I get 1/2 du. Right. If you, this means that 1/2 du is dx. Right. Dx is 1/2 du. So I replace dx with 1/2 du. The 1/2 I can pop out, du is here.
I just don't understand where the 1/2 comes from.
I want to substitute dx with something in du. Right? You agree du is twice dx, right? And you can think of these as differentials. You can think of du as twice dx, right? So what does that mean? That means that dx is 1/2 du, right? Okay? Remember, I want to change this to a guy with du in it. Okay? And that's more direct. Now, if you don't like that, there are two alternatives. You can use compensation, that's what most people do. Or, once you get good at this, as you get more comfortable with integrating, guess and check, which means I would accept answer only. And it hinges on this idea that we can differentiate the check, all right? Because here's the idea. I'm going to go ahead and erase, well, maybe not erase, maybe I'll go over here. Okay, you're asked to integrate sine of 2x plus 1 dx, all right? I claim that once you get good at integrating, once you get practice on the homework, you should be able to do this in one line, okay? Pretty much by guessing well. And in fact, in Calculus 2, your Calc 2 instructor will routinely do this in one line and won't actually show the use of. Okay? It'll be assumed that you can do this in one line mentally. Okay. Well, of course, we have the plus c. That's straightforward. All right. And what's the idea? Whatever the answer is, when we differentiate it, we better get the, what's the I word? The integrand over here. We need the integrand over here. Well, here's the deal. Whose derivative is going to be sine of blah? Well, it's going to be something like negative cosine of blah, right? And you can differentiate this to check, all right? Now, when we differentiate this, okay, if you differentiate this, we're going to get, okay, the derivative of negative cosine is sine, and then 2x plus 1, but wait a minute. What's the tail? The tail is 2, all right? This is not that. We're off by a factor of 2. So how do you think I pay for the 2? A 1/2. You see what I'm doing here? It's a thought process. Whose derivative is that? And by the way, you know, it's sort of adaptive. If you make a mistake, if you forget the negative sign, you forget the 1/2, okay? And go back and correct the mistake. So it's like a repeated guess and check, all right? Keep guessing at it until you get it right. Okay, you might be off by a sign or a 1/2 or something. Okay. By the way, it's not a coincidence that 1/2 is the reciprocal of this linear coefficient. Generally speaking, the reciprocal of this guy will be over here. All right. Trust me, once you get good at integration, okay, you're going to get quick at this. Okay, and some of you may be able to do this in one fell swoop without actually showing the u sub. However, I want you to show work when you're doing a u sub, except in cases like these, you don't have to show work. Well, what's the special case? Guess and check is okay, as far as I'm concerned, okay, if u is linear. If it's a linear function of the original variable of integration. So here, if you were to get the integral of sine of 2x plus 1 dx, okay, what would the u sub be? The u sub would be 2x plus 1, right? You agree that's linear, all right? In a case like this, you should be able to guess and check pretty quickly, and I'll accept that, okay, answer only, without you having to show me the u sub. If you want to do the u sub, that's fine. How would I tell anyone, right? want to do the u sub, fine, but you don't have to. Again, if a u sub is appropriate, you don't have to show me the work for it. You can use guess and check if the u sub is what? Linear. It's linear. Now, if it's like x squared or tangent of x or something, you better show me the u sub process. It's like writing an essay. I want you to write out the process. Okay? Again, I don't care if you're the Jake Gyllenhaal genius from Day After Tomorrow. You have to show me the work. It's like writing an essay. Okay? But if the u sub is linear, then yeah, your Calc 2 instructor will expect you to be able to do this in one line. All right? That's the rule. If the u sub would have been linear, you don't have to show me it. You can do guess and check. And that's fine. And again, some of you will get good at doing that. Others of you will go, nah, I want to do the u sub. That's fine. Just be aware that in Calc 2, your Calc 2 instructor will do this routinely in one step. All right. Question?
In yesterday's class, you said common choices for the u, and you put an exponent as one. How can an exponent be
Oh, I'll give you
an exponent?
See, that's going to come up in chapter 7.
Okay.
Yeah, that's when we do something like this. The integral of x 2 to the x squared.
Oh, okay.
Yes. The problem is that you don't know how to integrate 2 to the u yet.
Okay.
But chapter 7 we'll do that later. Okay. Here we let the u sub be the argument, which is very common.
Okay.
Right? Okay. But again, since it's linear, it turns out you don't have to show me the work if you don't want to. I'll accept guess and check. All right. Questions? Anything else? Yeah.
So you got 1/2. So is it always be 2 or 1.5?
Okay, no, by the way, one side note. Because I now have the 1/2, this is no longer in play, right? Because you get killed by that. All right. Now, are you asking about how I guessed at that?
Yeah, whatever.
Okay, yeah. So let me repeat this. Okay. Now, you know that when you integrate, you're going to get like a plus c, right? That's easy. Okay. And then you have to ask, well, whose derivative is sine? Is it cosine? Well, wait a minute. The derivative of cosine blah is negative sine blah d blah. Okay, well, I better put a negative sign then. All right. What's the derivative of this? It's going to be this. The sine of 2x plus 1. Ooh, but there's a 2 though. Right? From the tail. Right? There's a 2 from the tail. There's no 2 over here, right? He doesn't count. There's no 2 over there, right? So, you know what? I think I'm going to need 1/2. And then when that happens, you get this. Takes care of it. And again, you might not believe me now, but as you get better and more comfortable with integrating, some of you will be able to do this in one line. You can do answer only. Okay? And again, if this is linear, right, the coefficient's reciprocal, okay, is basically the key fudge factor. Okay, so that's the pattern you get used to. Now again, some of you aren't going to be comfortable with that. That's okay. It's just that when your Calc 2 teacher does it in one line, don't freak out. Okay, just trust yourself that you can do the use of it. Right. So if you never get good at guess and check, fine, you can get by without it. But you just show the work. It's always okay to show work. All right. But your Calc 2 instructor will do this in one line. Don't freak out when that happens. Questions? If you want some practice, go to wolframalpha.com. That's new. Put in an integral, guess and check. So if you want some practice, go to Wolfram Alpha, where you have a linear argument. All right. Now, u subs can get more complicated, really. Because this was easy, right? U subs linear. This is easy. I'll accept the answer only. This one's harder. Okay, Sokowski left in for number 38. All right. The integral of sine of 2x, secant to the 5th 2x, dx. Oh, trig. All right. Integral of sine of 2x, secant to the 5th 2x, dx. All right. Now, there's no immediate identity which will help us, cancel, for example, here. But we can still use trig identities. All right. The tricky part here is how to rewrite this thing in a useful fashion. All right. Equals integral. Well, I don't like secant. I'm more used to his reciprocal, who is what? Cosine. Okay, let's write this in terms of sine and cosine. All right, we have here sine of 2x. Because of this, this goes over what? Cosine to the 5th. 2x. Don't forget your dx. Don't forget that. You will agree. These are equivalent. Okay. this help us? Again, what do we want the u sub to be? We want to be a guy who's in there, whose derivative is also in there, up to a constant factor, or maybe a sign. All right. Now, the thing is, you want to play Goldilocks here. You want to get the u sub just right. Okay? Because here's the thing. Some of you might pick u equals 2x, which is not wrong. That will be helpful. But if you do this, it's too small. You're going to have to do a double sub. You're going to have to do another substitution down the line. Okay? So if you do this, u equals 2x, then eventually you're going to need like w equals cosine of u. Okay? Now that's not wrong, but it's a double sub, and I think most of you would prefer not to do a double substitution. By the way, I'm using a w here. I'm not using v. There are two reasons. For one thing, a lot of you people have v's that look like u's. Okay? That's one reason. There's a second reason. U and v are used in integration by parts. So I don't want to confuse things with that. That's why I put w there. All right. Again, a double substitution is not wrong, but I think most of you would rather do it in one fell swoop. Okay, so not wrong, but maybe inefficient. It's inefficient, not wrong. It's inefficient. All right. But then you might go, oh, okay, well, how about this? Why don't we let u be that whole denominator down there? Cosine to the fifth 2x. Let's let u be that whole denominator. What's the problem with this? Du equals, how do you feel about taking this guy's derivative?
We can do it, but
I hope we can do it. He's right, but it's going to be a mess, don't you agree? And whatever mess we get here, I don't think we're going to see all those guys in there, right? Okay, so du is mess dx. Now, that's not good work. I'm just saying that this probably won't be the best way to do it. Because I don't think that the derivative here will be seen clearly and cleanly in that integram. So this is too cold. He's too small. This is too hot. It's too big. What do you think might be a good choice for u? Yeah, that's just right. U equals cosine of 2x. Although again, the double sub here is fine. I won't mark you wrong if you do it correctly. All right, it's just inefficient. All right, u equals cosine of 2x. It turns out that this is the Goldilocks choice. Okay, it's just right. Okay, it's big enough so that we're efficient. We just need one substitution. But small enough so that his derivative is basically in there. Okay, up to maybe a constant factor or a sign. All right, du equals, first of all, don't forget your dx. I'll put an arrow there. Remember, I have the right to mark you down if you get your form wrong. Okay, this is conventional form. Put the dx in. Okay, just like the plus c before, right? Okay, now, be careful, you're taking a derivative. Okay, wait, so you're saying that as part of integrating, we're going to take a derivative? Yeah. Okay, so be careful about that. You're taking a derivative. Okay. What is the derivative of cosine of 2x? Negative 2 sine of 2x. The derivative of cosine blah is negative sine blah d blah. You all agree? Negative 2 sine 2x dx. All right. Question so far. Question so far. This is a case where the compensation method is clearly superior. By the way, I would not accept guess and check here because our u sub here is not linear, it's straight. So I would not accept guess and check. You must show me all the work, all the u sub work. Even if you're a genius, doesn't matter. All right, so let's use compensation. That's by far the best way to do it, I think. Yeah.
well, I just want to reinforce from the last problem that du equals negative sine 2x dx. There's sine 2x dx would equal negative 1/2.
That's right, and you know that's what I call the Kill Bill way, method 2. Yeah, basically you're right. This thing here would be negative 1/2 du. Now if you can see that, that's right. That is right. But you know what? A lot of people don't like doing that. They don't like the idea of Paul's saying, well, we just solve for that. That's method 2, and that's fine. That would work. This is negative 1/2 du, and that would work. And then down here's u to the fifth. That would work. But it's not the method that makes most people feel comfortable. But that makes, if that's good for you, pick your poison. That's fine. That's fine. Whatever makes you feel comfortable. And again, guess and check, no good. as far as I'm concerned, because this is not linear, so I want to see the work. Okay. Look, folks, some guessing is okay, but don't guess all throughout the test. I got to see some work. All right. This is not just linear. I want to see the work, even if you can do it quickly. All right. Let's do compensation. Okay. So where are we? We're over here. All right. Okay. I'm going to rewrite it anyway. Basically, equals. Put a space here. Integral. Okay. Fraction bar. Dx. Leave some space over here. Sine of 2x. You can always leave space. Over cosine to the fifth of 2x. Some of you might be, well, I don't know if it's whining, but some people might whine, yeah, but do we have to rewrite it? You know, it helps. Okay, because the compensation trick, I think, is by far the most comfortable one for people. People tend to like it. If they have to integrate. Maybe they'd rather eat a chocolate cookie, but... okay, but, if they have to integrate, compensation is a nice way to do it. All right. It would be great if we had what? Look at du. It would be great if we had what in our integram? What's missing right now? Negative 2. Oh, okay. Right now we're missing a negative 2. We need to get the du in there, right? Okay. So right now we need to get a negative 2 in there. Right. That's so that all of this can become du, right? But, and you mentioned this, how do we pay for the negative 2? Negative 1 half. Negative 1 half. Right? So we're basically multiplying by 1. Right? So this whole trick of multiplying by 1, you know, that's how we rationalize denominators, converted units, you know, if you have an imaginary guy, right? Likewise here we're multiplying by 1. Now you agree that this family of functions is the same as that family of functions, right? I haven't changed the family, right? Okay, I have not changed the value of that integral, basically. Right? Questions? Okay. Okay, now, in the next step, I'm going to go to u. All right? I'm going to go to u. We have negative 1 half out here. Integral. Okay, we don't need the plus c yet, because that integral sign's still in there. All right? What does negative 2 sine 2x dx all become? That's all du. Okay, and you can put it on top. Okay, it's okay if du is a quote-unquote factor of the top, or if it's out there. You never put it at the bottom, though. Comment. You never write du or dx or dt or whatever in the denominator. That never happens. Okay? So you can put du or whatever up here or out there, either way. You can put a du out there, put a 1 here. All right, over, what does this stuff become? U the fifth. You agree that looks a lot nicer, although some of you may have forgotten how to do it, but questions? Questions? We'll make it a lot nicer. Yeah.
You know the dx at the very end?
Okay.
Do we like split, when we place it there, do we split the difference between like the numerator and denominator, or does it, you know what I mean? Does that matter?
Is there splitting the dx or something?
Well, just like its placement, like where it's oriented in relation to.
Oh, I see what you're saying. Well, no, the idea is that, you know, if you have something like 4x over 3, you can write this as 4/3 x. It's 4/3 times x, right? So basically the dx, it's kind of like you're multiplying by him.
So you can move it around, it can be.
No, you can write him as a quote-unquote factor of the numerator, but not the denominator. You never put him in a denominator. You put him in the numerator, not the denominator. Okay? And if the numerator has more than one term, put grouping symbols. Okay? Like if you have x plus 2, put it in grouping symbols, and then your dx. Okay? So you can kind of treat him as a factor of the numerator, although some professors might object to the idea that it's a factor. Technically, the idea is that we're integrating this guy with respect to x. But mechanically speaking, we can treat him like a factor. Okay, but remember, if you have 4/3 times x, the x can go up there, but not down there, right? Okay. Same thing with dx. Dx has the same algebraic properties. Right. Okay. By the way, dx, when we explain what an integral is, dx later on will be delta x, like a small change in x, and then you can think of it more algebraically. Right now it's very symbolic. We're very lucky that these symbols work out. Anything else? Yeah.
I don't know whether or not this is longer or shorter, but you could pull out a secant tangent from the initial integrand, and so that you end up with integral u to the third du.
You can play those kinds of mixing games, right? So it's like you take out 1/6 secant, and then so tangent of 2x. Oh, but then you have tangent of 2x, secant of the fourth 2x, and then maybe use Pythagorean. It gets a little bit iffy.
I did secant 2x times tangent 2x times, but do you want to look at my work?
Yeah, but then there's like, what is
We have a family science
wait, 3, 4, 5. Secant tangent, and then secant cube.
And then another secant
U
at the
equals
end.
secant.
And then I made
Oh, okay, wait a minute. So U equals,
u
U equals secant of 2x. U equals secant of 2x. But still, that works, I think.
Yeah.
Yeah.
And then du would be secant x tangent x.
So, but be careful, okay, so secant of 2x. I think your method does work. But generally speaking, we have to be careful with high powers because in Calc 2, you're going to deal with more of the high powers. Sometimes you need like Pythagoreans or something, right? But no, I think what you have there works, but you use 2x.
Okay.
Now, by the way, especially for trig functions, you might do it one way, your friend might do it another way. You get different looking answers. You both could be right. Why? Because all those trig identities, right? So, you know, and that's why my pink sheets have lots of different ways, different forms for the same family of functions. You can even be off by a constant term. It doesn't matter. Plus c times 1. Alright. So, bear in mind there might be different forms for the answer. And on the pink sheets, I try to get different appropriate forms. Alright, we're over here now. Do you remember how to integrate this? We should rewrite this. 1 over u to the 5th. How can I rewrite that?
Use the negative fifth
Yeah.
u.
Yeah, and that's easier for us because we can use the power rule. So remember, when we're differentiating or integrating, we actually prefer the negative exponents to that. Alright. Negative 1/2 integral u to the negative 5 du. Okay. And notice that I have not yet integrated, right? I haven't technically integrated yet. This is all part of the big process. Finally, I think we're ready to integrate, meaning I'm going to remove the integral sign, remove the du. Which means I need to write what at the end now? Let's see, don't forget that. So remember, at any stage, you're either going to have the integral sign and the d blah, or you're going to have the plus c at the end. All right, any questions? We're finally going to actually integrate. So far it's been set up. Okay, right now we're actually going to integrate. All right, with respect to u, negative 1/2. Okay, straightforward. Integrate u to the negative 5th. U to the negative 4 over negative 4. All right. Be careful. All right. A negative 1 here, negative 1 here, so bye-bye, right? Okay. Careful. 1/2 times 1/4. That's 1/8, right? Careful. All right. U to the negative 4. That's 1 over u to the 4th. All plus c. You all buy that once you make this thing nice, 1 over 8 u to the 4th, all plus c. Any questions? Be careful. Okay. It'd be kind of embarrassing if you made a mistake on the algebra things. Okay. So, well, let's see now. I can write this as 1 over 8. Well, what was u? U was cosine of 2x. Cosine to the 4th of 2x. Do not put the 4 on here. Not here. Okay, wasn't that in Family Circus? Not me? Not here. Do not put the 4 over there. Okay, that's cosine of the 4th power of 2x. That's completely different. Right. 8 cosine of 4 2x. Don't forget. Plus c. And we generally try to make these things more compact in the sense that if you see 1 over cosine of the 4th 2x, we normally rewrite that as how? Secant to the 4th 2x. All right. So we have secant to the 4th of 2x over 8, or you could make it 1/8 times that, right? Plus c. Okay. And I can't say you can make this any nicer. You cannot cancel here. All right. So basically 1/8 secant to the 4th 2x plus c. Now, if you're brave, you could differentiate to check, although you would have to use some identities to get it back to the raw original integrand. It might be trickier to check this, but you can do it with some trig identities. All right. Sometimes the check might take longer than the actual problem, depending on what's involved. Questions?
So if you left it as 1 over cosine, would that be wrong? We have to do it in two pieces.
suffice to say this is preferred.
Okay.
Would I mark off? This is generally preferred. It's considered simplified compared to that. So I would have a right to. Would I do it? Questions? Questions? Let's do another one. This one isn't so involved, but there's a trick. But it's a good trick to know, because in Calc 2, you're going to deal with a number of these manipulations. All right. So this is tricky in a different way. Not because it's involved, but because there's a fundamental trick here. Integral of x root x minus 1 dx. All right. Now it's easier if it's like this. There's a homework problem like this, right? Then you can, make the integrand nice and integrate. Okay. But this is trickier. Remember, you cannot distribute the x evenly. All right. So what's another way we can do this? We can do a u sub. Let u be the inside guy. What do you think I mean by that? X minus 1, right? Because that's kind of irritating, the fact that there's a binomial there. U equals x minus 1. Oh, but then what's du? It's just 1 dx, right? Du is dx, right? Du is 1 dx, du is dx. So, what is this? Equals integral. Okay, so this piece here, fine. This becomes the square root of u. Dx is du. So far, so good. But then, what's the question you want to ask?
What happened to x?
How do we deal with x? Well, look at this. U is x minus 1. What's x? X is u plus 1. Solve for x. That is a trick. You can solve this substitution statement for x. And that's legitimate. All right. U is x minus 1, therefore x is u plus 1. It helps that this is a one-to-one guy, right? One-to-one function. All right. So x is u plus 1. Is that right? I need what? Big symbols. I forget that. A lot of people forget that. Okay, whenever you're doing a substitution or replacement, be prepared to put grouping symbols unless you're sure you don't need them. And at this point, this should be a routine problem, but I will go through this. Any questions?
A little bit, John. Back over here, when you went from the top step to the middle step,
Okay.
what happened to the du? And,
Okay, I'm actually integrating. When you're actually integrating, you remove the integral sign, you remove the d block, you put the plus c. We're actually integrating at this step.
and then, right. I got you.
And it took a while, but eventually we got there. It was set up. Up until there it was set up. U subs are a big setup. Over here, you know what? It's okay if the junk's out here, okay? Because now we can distribute easily with this guy. All right. So this guy equals, I should put this, integral, let's do it this way. U plus 1, in parentheses. The principal square root of u is u to the 1/2. Du. What's that d word? Distribute. Use the distributive property. Okay, this works. Now bear in mind, not everything distributes over everything, but multiplication does distribute over addition. Your old algebra rules still work here. In fact, a lot of you are going to need to remember your algebra. Okay? Okay, all the things you learned back in 46 and 96, they still apply. All right, equals, integral, grouping symbols. Remember, if your integrand has more than one term, you need grouping symbols. All right, what's u to the first times u to the 1/2? U to the 3/2. And hey folks, if you need to do some side work, be my guest. Okay? I'd rather have you do side work neatly on the side than get it wrong. All right, plus u to the 1/2. All du. And finally, we're ready to actually integrate. Before that, it was all set up. Any questions?
If we go back to one step over there, can you do another substitution for u, like say dw?
Here a substitution wouldn't help so much, because if you do it here, then you're going to mess that up again. You're going to go back there, basically.
Okay.
You're going to go in circles. Okay, so it's okay for this guy to be messed up. You need the radical to be nice. Okay. Because you can distribute this way, you cannot easy this way. Okay, and even if you did do it, then how would you work it out then? All right, we know we can work this out. We're going to actually integrate. We're going to remove the integral sign, remove the du. We're going to put what? Plus c. Careful, integrate. How do you integrate u to the 3 halves? U to the 5 halves over 5 halves. Plus, integrate u to the 1 half. U to the 3 halves over 3 halves. You sound thrilled? Okay. All right. Some of you can do this quickly, but I say be careful. Okay. When you divide by 5 halves, you're multiplying by 2 fifths. 2 fifths, u to the 5 halves. Plus, when you divide by 3 halves, you're multiplying by 2 thirds. U to the 3 halves. Plus c. If you want, you could tuck these into the numerator. That's fine, but not the denominator. All right. Finally, we have to at least unravel this. Your final answer should not be in u. It should be in terms of the original variable. So you have to go back to the original substitution now. Use that. 2 fifths. This is x minus 1 all to the 5 halves. This does not distribute over the difference, so this is good. All right. 2 fifths, x minus 1, that's all to the 5 halves. Plus 2 thirds, x minus 1 all to the 3 halves, all plus c. A lot of books like to factor here. I'm indifferent. I'm okay with this. All right. But some people factor out this and maybe a 2 or something. Maybe a 2/15. All right. 2 fifths, x minus 1 5 halves, plus 2 thirds, x minus 1 3 halves, plus c. Okay. And for some reason, even Mathematica has a hard time doing these kinds of problems. So right now, you're smarter than Mathematica. Okay. All right. And you can differentiate to check. Although if you check it, then you're going to need to use an algebra. All right. Practice makes that perfect. Better. Questions? Questions? You're going to want to practice, but you'll get good at it. All right. In fact, some of you are going to get so good you can actually do guess and check when the use of is linear. All right. Okay. We're on schedule. We normally do have a lot of questions about the use ofs. Any questions? Get practice. All right. Get practice. You can get good at this. All right. We've been talking about indefinite intervals, where the answer is a family of functions. Right? So, for example, before we were doing stuff like this, right? The integral of x squared dx is what? X cubed over 3 plus c. Okay, that's a basic one-point indefinite integral problem. All right. So basically, your answer is the set of function rules whose derivative is given by x squared. All right, so your answer here is a family of functions. All right, this represents a family of functions. Okay, represents a family of functions. Okay, now that's an indefinite interval. What's a definite interval? All right, so if Sulkowski defines a definite integral in 5.4 and discusses properties in 5.3. I'm going to flip it.